Right then, this probably covers about 2 lessons worth of content on the acyl group and acylation. So we're going to start with the basics, and then there's some practice exercises and some example mechanisms. So then, acylation, the verb, refers to transferring an acyl group to another substance. And there are a number of different ways that this can happen, but there's one we're going to look at to begin with. Okay. So acyl group is not necessarily a kind of thing we're familiar with, and this diagram will help a little bit in understanding that. So if you look at the general structure, R, C, O, Z, R represents an alkyl group, so any number of carbon atoms attached to hydrogen atoms as appropriate. The C double bond O, that's a carbonyl group, and this section that we're looking at now usually comes at the end of the topic on the carbonyl group. And then there's something called Z, which is just to match the textbook's kind of formatting. That's something that we call a leaving group. Okay, so the acyl group is basically the part of this structure that's outlined in blue. Okay, so it's the RCO part of it, as you can see in the key. Now, that structure cannot exist on its own. The point is that it has to be attached to something else, so there has to be something else bonded here where this carbon is. But the process of acylation is transferring that section, the R, the C, and the double bonded oxygen, to something else. Okay. In the process, Z, whatever that is going to leave. That's why we call it a leaving group. It's going to get kicked out of the original molecule. This all will make a bit more sense later on when you're looking at actual examples. For now, it's just something that you should pause the video and copy into your notes. Okay, so just to sort of highlight this a little bit, the following diagram is not useful in terms of mechanisms or actual reactions, but it's just to kind of reinforce what we were just discussing. So acylation is the process of adding an acyl group to another molecule or transferring an acyl group to another molecule. So what we've got here is, let's move that out of the way, Z, which is what the acyl group is originally attached to, leaves and is now on its own. X, which the acyl group was not attached to before, is now attached to the acyl group. So that's what we mean. We say that X has been acylated. We've added an acyl group to it. And that's kind of generally what this is all about, transferring this portion of a molecule around. Because remember, that bit is the acyl group, RCO. Okay? So, the kinds of compounds that can do this are called acid derivatives because they're derived from carboxylic acids. The first one that we're going to look at is the one that we're going to spend the most time with, which is a class of compounds called acid chlorides, which are interchangeably called acyl or acyl chlorides. So just to be clear, those two names are for the same thing. Acid chlorides is one name, acyl chlorides is another name, same molecules. They have the generic structure that's very similar to the one at the beginning, but instead of there being a Z down the bottom, there's now a chlorine. If you were writing their condensed structural formula, which is something you will have to do as part of equations, then you would write RCOCl. So the simplest example of one that you usually look at is ethanoyl chloride. There is also methanoyl chloride, but it's not very stable, so we don't tend to get asked very many questions about it. So ethanoyl chloride, the suffix for an acid chloride is oil chloride. Okay. Generally, their structures tend to be pretty straightforward. In other words, there's not usually other stuff in the chain. Okay. This one has 2 carbons and no double bonds between the carbon atoms, so it's ethan oil chloride. Its condensed structural formula would be CH3COCl. Your turn. Pause the video and try drawing the displayed formulae of the 3 acid chlorides that are named on the right. Okay, so if you've had a go at those, just to double check. Propanoyl chloride, 3 carbon atoms. Okay, methanol chloride, 1 carbon atom, so there's only really room for a single hydrogen. Okay, this is kind of like when you have methanoic acid or methanal. It can look a little bit weird, but that's right. Okay, quick reminder that methanol chloride is not very stable, so we don't really look at its reactions, and generally speaking we tend to stick to ethanol or propanoil chloride. But anyway, butanoil, 4 carbon atoms this time, and the appropriate number of hydrogens. Okay, so our next class of acid derivatives which act as acylating agents are called acid anhydrides. These ones look quite scary, right? But they're not actually that bad. Having said that, the AQA don't spend very long with them. Generally speaking, it's equations only with these, and you don't usually do mechanisms with them. Okay? So an acid anhydride looks like that. Its condensed structural formula would be RCO in brackets 2O. Let's have a little look at what that's supposed to mean. So this section here basically reflects the fact that there are 2 acyl groups, okay, and then they are joined by a single oxygen, and that's reflected by that part of the condensed structural formula. So that's where it comes from. There are other ways that you can write these things, but generally this is a nice, neat and tidy one. Speaking of being neat and tidy, I'm going to get rid of these colours now, okay, because we're still going to continue to look at this structure a little bit more, and I wanted to clean it up a little bit. Okay, so acid anhydrides look a little bit scary, but realistically they're not actually that bad, and it helps a little bit if you know a little bit about where they come from. So although this isn't really what I'd call required knowledge, I do think it's helpful. So acid anhydrides are formed from the reaction of 2 carboxylic acids. So if we say we have 2 carboxylic acids that look like that, and we take away a water molecule from them, and they are then joined together, so this is effectively a condensation reaction, you get the structure that's on the left. It might not look obvious, but you do, right? This carbon atom here is now this one down here, and it's joined to this oxygen, which is now this oxygen. That's what we're basically saying, okay? So the name acid anhydride sort of suggests all this. Acid meaning carboxylic acid, anhydride meaning without water. Okay, so that's how they're formed. There's usually a question at this stage when people are in the lesson, which is what happens if the 2 R groups are different? At A level you never have to deal with this. All the acid anhydrides you encounter will have the same R group, meaning they were formed from 2 molecules of the same carboxylic acid. And realistically there's only really one you tend to look at, so let's look at it. So here's the one you're most likely to encounter, ethanoic anhydride. This would have been formed from 2 separate molecules of ethanoic acid that reacted together, and a water molecule will have been produced as a byproduct. There's nothing too complicated here, it's just instead of R we have a methyl group. I've not shown it as a displayed formula because it starts to get to the point where it's a little bit cluttered. If you were asked to draw the DF, obviously you'd have to show all the carbon-hydrogen bonds. So for the condensed structural formula of this, we have CH3CO in brackets 2O, and that follows the same pattern that the generic version did. So obviously as we go through the video you should be kind of pausing as appropriate to take notes. I'm not going to stop for any amount of time, so it's up to you to kind of control that. Right then, this is one of the ways that acylation can occur. We introduce a new mechanism here. The name of it is nucleophilic addition elimination. That name comes as a package. It is not separate, something you can separate. It is nucleophilic addition elimination, hyphenated. It's very easy to confuse this with nucleophilic addition because there are some similarities in the first part of the mechanism, and it's also quite easy to confuse it with nucleophilic substitution because overall it looks like a substitution even though it isn't. So there's quite a lot going on here, right? It's probably the most complicated mechanism you do in A-level chemistry. There's kind of the most moving parts, and naming the products can be difficult, so we're going to spend quite a long time looking at that in this video as well. All right. For now though, let's have a look at a general version of the mechanism. So RCOZ basically represents any acid chloride or any acid anhydride, okay? And we're just doing it like this to begin with to look at the principles behind the mechanism, and then we'll look at some specific examples. So our nucleophile in this reaction, there are a few that we'll look at. I'm not going to name them all now, but you'll see. But the thing that they all have in common is they all have at least one covalent bond to a hydrogen atom in their structure, because that's an important part of how this mechanism works. So if you've learned quite a few mechanisms already in A-level chemistry, you should be looking at this and you should be itching to do something already, right? You take it back to first principles, which is curly arrows originate at a pair of electrons and they terminate, or the arrowhead reaches a place of low electron density. So we go from a region of high electron density, which is a bonding pair or a lone pair, to a region of low electron density, which can be either a partially positive atom or a formally kind of positive, positive ion, for example. So what we should get is a nice curly arrow from the lone pair on the nucleophile to the partially positive carbon atom. The carbonyl group is polar. We already know that if we've studied the nucleophilic addition mechanism, right? The partial charges are not required when you do the mechanism in exam questions, but I always include them in the first example just to remind ourselves of how it works. So in this same step, there's also going to be another movement of a pair of electrons. Again, thinking about principles, the formation, the movement here that we've just described from the nucleophile is the formation of a bond between Nu and that carbon atom in the middle. That carbon atom in the middle already had 4 bonds, which effectively means that one of the bonds that's already there has to break. And the one that goes is one of the bonds in the carbonyl double bond. So we move a pair of electrons onto the oxygen. This is exactly the same thing as what happens in the nucleophilic addition to aldehydes and ketones. Okay, but the similarities are going to stop there. It's just that this first part is identical. And that's why the first part of the name of the mechanism is nucleophilic addition, because what's just happened is nucleophilic addition. We have added a nucleophile. Things start to differ though. We have this intermediate structure. So let's just look at where this has come from. There's a pair of electrons on the oxygen at the top of the molecule, which now has a negative charge. That's all essential detail. That's happened because we moved a pair of electrons from the carbonyl onto that oxygen. Z is still attached, and now the nucleophile has a positive charge. So this will make more sense when you're looking at the specific examples, but the idea here is we've formed an extra bond with this nucleophile. It's used its pair of electrons to form a coordinate bond to that central carbon. Carbon's not contributed anything, and that gives the nucleophile a slight positive charge. And all of this is going to be resolved in this step. So some parts of this are obvious and some parts of it are not. The part that's probably most obvious is we classified Z as a leaving group early on in this video. So it has to leave now, right? And the way that that's going to happen is the bond between carbon and Z is going to be broken. And it's going to be broken in a very particular way. The pair of electrons that's holding C and Z together is moving on to Z. Again, just to go back to sort of principles, that now means once that's happened, the carbon only has 3 bonds, which is also not right, right? We can't have carbon with 5 bonds and we can't have carbon with 3 bonds. So in this case, the way that that's resolved is that the carbonyl double bond is reformed. So this is where, one of the major ways that this differs from the nucleophilic addition mechanism. In nucleophilic addition, we would have had a curly arrow going from the lone pair on the O- to a hydrogen ion. And that doesn't happen this time. We don't form a hydroxy group with that oxygen. Instead, it's reforming the double bond. At the same time, our third and final curly arrow for this section indicates movement of a pair of electrons onto the nucleophile to satisfy that positive charge. Okay? Effectively, the nucleophile is going to get its lone pair back, which means that the hydrogen is going to be leaving too, but it's leaving with nothing, and that makes a difference to the byproducts. So those are your three curly arrows. Again, the idea will be the same each time. No matter what the nucleophile is and no matter what Z is, it'll be very similar. Let's look at what comes down at the bottom. Okay, so we've got a double bond between the carbon and the oxygen again, a single bond to the nucleophile, which is now attached, a hydrogen ion with a positive charge. Let's go back for a second. Right, this has happened because the electron density, the pair of electrons that's holding the nucleophile and that hydrogen together, has moved onto the nucleophile. That leaves the hydrogen with nothing, right? So the hydrogen has a positive charge. Okay, so you can kind of imagine you're tracing your electron density, your pair of electrons, onto the nucleophile. Z has a negative charge. That's because the opposite's happening here. This pair of electrons that holds C and Z together is actually moving on to the Z, which means it ends up with an extra electron, which is what gives it a negative charge. If this stuff's bothering you, again, you could take it back to sort of first principles, right? Remember your GCSE idea that a covalent bond is a shared pair of electrons. I'm not going to draw out an entire dot and cross diagram, but if you just look at the bond between C and Z, if you then take that pair of electrons and stick it on Z, which is what we've basically done, Z now has an extra electron that it didn't have originally, the one that's the dot or the cross, whichever way around we had it. That leaves the carbon without one, but because the carbon reforms its double bond with the carbonyl, it doesn't end up having a positive charge. Okay? It's the same principle with the nucleophile and the hydrogen. Right then. Only other thing to add here is that I've put H plus and Z minus as something separate. In reality, you'd usually show that as a compound, right? Where you're not showing the charges. Hydrogen is attached to Z, whatever that is. Right then, so there's the mechanism, right? Obviously there's a few things that can go wrong there, but it gets more complicated as we go along. And let's have a look at our first example. So here's ethanol, chloride and water. This time I'm going to say to you, pause the video, copy the structures, do the first two curly arrows, because there's absolutely no reason now that you can't do those. So once you've had a go at those, which you should have done, we have those movements, okay? I've drawn my water in a particular orientation. If yours wasn't, for example, if you were going in blind and doing this from scratch, rather than copying mine, that would be totally fine, as long as you get the kind of origin of the curly arrow and, you know, the destination of the curly arrow correct. It's just that it's easier sometimes to do mechanisms in a particular way, so I always set them up in the easiest way. So then, here's your intermediate. Using the information from the generic example, pause the video, copy this and draw three curly arrows. Okay, so you should have done that, and you should have got reforming of the double bond, leaving group takes two electrons, we move a pair of electrons from a hydrogen, I've picked the bottom one, but it could have been the one on the right, doesn't actually matter, onto the oxygen. Okay? So then, our products. Quick reminder that we'd probably write this as plus HCl, okay? Instead of Z minus, we've now got Cl minus, but it's the same principle. This thing on the left, you should be able to name it, so pause the video and name the organic product. So what we should have is ethanoic acid, and then we'd call this probably hydrogen chloride because it's probably going to be evolved as a gas, but if there's any water around for it to dissolve in, you could also call it hydrochloric acid. I'm just going to call it hydrogen chloride for now. So then, The equations for this combination look like this. The top one of the two is for ethanoyl chloride and water to make ethanoic acid. The bottom one's just there again as a generic thing. Any acid chloride will react with water to make the corresponding carboxylic acid and hydrogen chloride. So you can pause and copy those, and then there's just something we need to discuss. So then, in this topic, in the notes online and in the textbooks and stuff, you'll often see like a table of equations that say, if you mix an acid chloride and water, you get these products. And that's fine, you know, you can learn all that if you really want to, but in a lot of ways it's easier just to learn the mechanism well and to learn some of the principles, and then you're going to arrive at the structure anyway. So that's what we did, right? I didn't tell you up front that we were going to get a carboxylic acid. Instead, we just got to the structure by basically, you know, tracing through the mechanism. And actually, I do kind of recommend that for this topic, just because there's so many combinations. If you really want to, you can make some flashcards and you can, you know, figure out how to learn the, you know, the products just from sort of memory. That's fine. It's just that there's so many other things to learn in A-level chemistry that I'd probably avoid it myself. But it's your call. I'm just saying I don't recommend it. I recommend learning the kind of principles rather than just the products. Okay?